So for today's lecture, we're going to do the example of torsion that we showed last week, and then we're going to switch to shear actually, and then after the shear sections, we're going to switch back to thin wall of torsion. And the reason for that is I didn't realize that thin wall of torsion actually relies on a couple of things that we're going to derive during the shear sections. So we can regard torsion of thin wall sections as a special case of the shear. So with that said, let's examine our problem that we stated last week. And with this, you have a circular beam. In this case, it's a thick wall beam with given radius r. You have given that the shear stresses in x, z, and y, z are equal to minus ay and ax. And they say the question is use the shear stresses to determine applied torsion to the beam. So go back to our lecture slides. What we have to do is go back to the previous slides.
It's a solid beam,
yeah, it's a solid beam. So what we have to do is we basically come to this equation that we have here. So we have already the equation of torsion given, and we know it's a function of phi, which is a Prandtl function, and we know that phi has a certain characteristics of how it's defined. So of course we go back again. This is actually where the equation, this is the equation that basically eventually is used to calculate phi or calculate the bottom equation, the torsion. If we go one step further, we know actually that relies on tau yz and tau xz. So that's the equation that we're going to use in our solution approach. So in this case, the second from the bottom. So let's do that. We have our torsion from our lecture slides and previous derivations. So it's double integral of tau yz multiplied by x minus tau xz multiplied by y, and then we have dx dy. So we will do a couple of things. First, we recognize that tau xz and tau yz are actually given. So tau yz is equal to ax, and tau xz is equal to minus ay. So we substitute the two given equations into our torsion equation to get the following equation. So we get ax squared, and the minus cancels out, becomes a plus ay squared dx dy. So since we have a circular tube, we're given radius r and coordinate system xy, it's easier to basically do a coordinate transformation instead of doing x and y going to r and theta. So if we do a coordinate transformation, we can define the x coordinate as cosine or r cosine theta, and we can define the y coordinate as r sine theta. So what happened to this, to the integration bonds? So if we do that, our integration bonds basically become, so our dx dy, they become r dr d theta. And with that said, we can now substitute our x coordinate, our y coordinate, and our integration bonds to get the following equation. Then we get r squared cosine squared theta plus dr d theta. And of course, since we basically went from an xy coordinate system to an coordinate system that depends on r and theta, we have to change the integration bonds. So basically it goes from 0 to r and 0 to 2 pi. 2 pi basically is the whole radius, or the 360 degrees. With that said, we can rewrite this equation that we have here slightly differently. We can basically take r ar squared out of it. We can multiply by this additional r, so get ar to the third. And then we get cosine squared theta plus sine squared theta dr d theta 0 to 2 pi. Well, technically 0 to r and then 0 to 2 pi. Okay. So what do we know from our unit circle? Basically, we know that cosine squared plus sine squared theta equals 1. So we can rewrite this as just 1. So this equals 1. So what do we have? We have our double integral. And we have ar to the power of 3.
Professor?
Yeah.
Why did you change the order of the integrals?
If I'm correct, since this is the first integration, this is the 0 to r with the dr, and then it comes 0 to, yeah, this should be also 0. Okay. That's actually, if I'm correct, that's the order of integration. Which one comes first? That will be a first one, and then the second one is just the second one. If I'm correctly. 80% correct about it.
So does it matter if we switch?
It doesn't really matter. It matters after you do the evaluation. You just make sure that you do the right integration. Just more convention. But say, for example, now what you now do is you take the derivative. You take the integral with r, so you get officially you get ar to the 4, right? And you evaluate from 0 to r. So that's your first step that you do, and you say 0 to 2 pi. So now it matters where you define this correct bound, and it becomes, of course, easier. You just have to make sure that when it's a dx dy term, that you don't forget confuse which bounds are you taking for which term or which variable.
If we integrated the theta part first, would it matter?
No, what you say, for example, if you integrate the d theta, it doesn't matter. So you can say ar to the power of 3 theta, and then you just make sure that you define 0 to 2 pi, and then you left over the 2 dr integral bound and 0 to r.
So the limits are interchangeable.
Yeah. The integration doesn't matter if you integrate first with x and with I.
And so I understand you're dealing with a circular bar or circular rod over here, but our shear functions were in the x and y directions, and the function we use over here was also in the x and y direction. What would happen if we could just straight away?
You still have to, in this case, then you have to come up with integral bounds from, say, 0 to y and 0 to x.
So it would yield the same.
It will yield the same final answer. It's just the integration about, and a circular cross section about x and y is significantly more difficult than doing the quantum transformation and going from 0 to theta.
So would the limits be like plus y to the negative y, or?
It depends. Like if you go from the circle and say, yeah, you can go from basically what's r at all the interlocations. So probably you will have say a minimum bound and a max bound. Yeah. It depends. So yeah, let's take the integral first with r. So we get 104 r, 104 ar to the power 4, and evaluate from 0 to r. So this becomes just 104 ar to the power 404. And then we can do the integral from the 0 to 2 pi of d theta. That one is a r to the power 4 over 4 theta evaluated 0 to 2 pi. So if you evaluate that, you get 2 pi. So basically, what we get is AR through 4 over 4 multiplied by 2 pi. So this torsion. You can simplify it, saying AR to the power 4 times pi over 2. So that's our final answer.
That's the torsion function.
Yeah.
So we could just plug in the R and get the torsion values.
Yeah. So we know that basically, keep in mind that this A, what we get here, is the coefficient A that was given here, right? So that's not an area. Just keep that in mind. In this case, it's just a coefficient. It's given B, C, D, E, whatever. So we know that the torsion applied, given the fact that we have chosen this phi. So you can even go a step first and then find what your phi is. So we said that tau yz, I have to call that again. So what's our frontal function? Tau yc is negative d phi dx, and tau xz is d phi dy. So you can basically also determine what this function is. So this was ax, and this was minus ay. So this derivative with x is ax. So this is probably phi would be something like this. Because now if you take the partial derivative with x, you get this one. So with x you get ax, and then partial derivative with y gives you, so this is equal to the minus the partial derivative, so the negative partial derivative of y gives you minus ay. So a question could be, what's also your test function that you used? And that will be using this coefficients and then doing the backward transformation. So but that's it. Okay. Most of the torsion problems that we will encounter actually in this lecture will be not about solids, but more about thin weld, and that will be basically covered after we cover the shear sections. And with that said, are there any questions regarding this section? We did a lot of derivations, I know. Once we go into a, say, thin weld section, we can do a bit more problems that's actually applicable to our aerospace structures course. Since there are not many solid tubes that you use actually. Okay, let's erase this. And then we go basically into our next topic, and that will be basically shear. And then from shear we revisit torsion for thin weld sections only. So let's take let me just actually pull up the right slides for you guys. So, yeah. If I need a slides, I can go switch easier. So the next topic will be shear. So basically what we have so far discussed is bending, torsion of solids. So far discussed is bending, torsion of solids. We'll discuss now shear. These are basically open / closed sections, thin weld as well. basically only thin wall. And then we go back to torsion, thin wall sections. So we have to make a jump to shear first, basically drive a couple of equations that we can reuse in torsion. Also can become a bit confusing. Big purple slightly better visible. Okay. So if we talk about shear, what do we know? So from statics, we know simply any applied load must equal to our internal loads, right? So if we have any cantilever beam, we apply a certain load and shear to it. Let's call that Sy. And if we would make a cross section here, we basically have an internal force. Let's call that V for now. And that internal force should be equal some way, somehow to our external applied forces. We just have to remain in equilibrium. So what we can do is, okay, once we identify that these two forces are equal, what will happen to the structure internally? Once we apply force to it, we will know that we will create some stresses, similar aspect as if you would have a rod. We said if we have a rod with a mass M hanging and we cut it, then we will have our forces that are in equilibrium. And then we can translate this force to a stress times area. We can do the same thing for our, say, shear sections. So let's redraw a slightly different. I'm going to draw a C section in this case. And it's clamped on this side. And we have a certain force acting on it, Sy. So if you look at it, if we would take a cross section out of it, and let's assume that we have a certain thickness to it, what we'll see is that at any sections, say if we take a small element out of it, we still have to meet the requirement of equilibrium. So we'll see it, we'll have a shear stress going up, and we can multiply that shear stress with our area, which is basically, let's assume this to be length S and thickness T. So we can multiply that shear stress with length S and thickness T to basically get our shear force out of it at that small increment. If we take the integral for the whole stuff, whole cross section, it should apply to our external force. So we can make a couple of things, assumptions out of it. We say that the variation of stresses, in this case of taus, can change on the cross section, but through the thickness remain constant. So may vary at any point. But tau is constant or does not vary in the thickness direction. Okay, so this means that if I would look at this side, say the outer edge, and I would look at point B, which is the inner edge, say tau A is equal to tau B. No variation. Yes?
So, the applied load is in the vertical upward direction.
Yeah.
On the C-beam horizontal parts, you have driven arrows that are pointing to the left and to the right. Shouldn't they all be pointing upwards?
No. I will get to that later. So yeah, you can technically say all the stresses should point upward because we have thins. Where we want to go is, my next point is actually, since if we would go to a say thick wall and we basically reduce this to a thin wall section, so we'll now say the thickness slightly smaller than 1. And if you would look at the same section here, what do we see now? So basically, we always neglect thickness, right? So we can say that, okay, I still have to maintain my, say, my area coefficient in order to get it equal to the force. So if I have my segment S and my thickness T, which is basically I can neglect, how do I get my area? So instead of now looking at shear stresses, we look at a different concept, basically at shear flow. And we identify shear flow as Q, and we say that's equal just to the shear stress times T. In this way, now we can say that force is equal to the shear flow times the segment we travel over. By assuming that the shear flow is equal to the shear stress times T, we basically have to take into account that we have to take the area. And this is basically a concept that we introduce to make our life simpler. Just more mathematically, to make our life and derivations and how we talk about structures a bit more simple. Instead of, we could do the same thing with shear stresses, but then it becomes a bit more complicated in our derivations. So we must recognize that now again, the shear flow or shear stresses around the thickness are still the same, or are still constant. But we also recognize that the shear flow and shear stress at the same point can vary from point to point in a cross section. So, for example, the say tau C and tau D, they're not different. They're not the same. So at any location, the shear stress can vary around the cross section. But within the thickness, they cannot vary. So that's basically what this assumption says. And then we go, instead of shear stresses, we look at the concept of shear flows, and we then identify the concept of shear flow being the shear stress multiplied by the thickness. So if you now look at this is unit Newton per, say, meter squared. This is multiplied by meter, so shear flow is Newton per meter instead of Newton per meter squared. So that's also the unit of it. And this becomes, again, a bit simpler to identify what we later on we will later identify as given a shear force. Instead of looking at the directly to the stresses what they introduce, we're going to look at the shear flows they introduce. And if we want to calculate shear stresses, we just multiply by the thickness of that location, and then we get our shear stress. And also make it a bit easier to introduce varying thicknesses in the cross section. So now the goal is, okay, how does the shear flow vary as a function of our shear force, Sy? By the way, shear force can also be, if we look at, depending which book you take, it can be V, it can be D, or it can be just S. So there are a couple of different, it depends on the notation. But in this case, we're going to go for Sy, shear force in the Y direction, and Sx, shear force in the X direction. So let's basically get rid of this, and then we're looking at a small incremental element, and we're going to see how the equilibrium equation vary, and how we can use those to our advantage to determine this function here. Say the variation of shear flows as a function of shear force. Say if we would take a small element out of this, we take this element, we'll have our element, and we basically can identify all the shear stresses on there. So let's go from stresses first. So this is z-axis. I will call this the s-axis. I will get to what s means. It's basically like as in the previous picture, just a small length. Okay. So what we get is, in this case, we have a sigma s. We are our shear force, shear flow tau sz. And then on this side, sigma z, shear flow direction, tau sz. And on this side, we get shear flow in z plus dz multiplied by delta z, and get our shear tau cs plus the variation of tau cs with respect to z multiplied by the delta z. And this side we get tau sigma s plus delta sigma s over ds plus multiplied by ds. And then we have the outer shear stress ds plus delta cs over s sigma s. And then we have to identify two more variables. This is this is dc. Yeah. And of course, what we will do is we can now interchange tau with q. So we're going to look only in one direction. Let's do in the z direction, and we write the equilibrium equations again out. So what we get is, assuming coordinates that this one pointing left is positive. Let's actually take our equilibrium equation first. So equilibrium in z direction gives us sigma z plus tau z dz multiplied by delta z. Again, we have to go multiply this by the area, so that's basically t ds, because this is our segment ds, so t delta s, and then this one is negative, so we get tau or sigma z times t times delta s, and now we have to take into account these two shear stresses as well. So what we get is plus, delta tau zs variation with s delta s, and we have also tau zs here, and again we have to multiply by thickness, and then in this case will be dz. And then we do minus tau zs thickness delta z is 0. So this is the equilibrium equation in the z direction. So what we do is we take every force, every stress in the z direction, we multiply by the area to get the force, and we take the equilibrium of that. We equate it to 0. So what we do now is actually we recognize or we assume as assumption that we said we use that Q is equal to tau multiplied by T. So this will give us the shear flow Q instead of tau. This will give us the variation on the shear flow of Q. And then this thickness disappears. Okay? So this one disappears. And here, this part is also replaced by Q. So this disappears as well. So this is our equilibrium equation. And of course, we have a couple of canceling terms. So sigma z multiplied by TdS cancels out with sigma z TdS here. So this and this cancels out. This Q multiplied by delta z cancels out with this Q and delta z. So this cancels out. And we get a reduced format. We get from our equilibrium in Z. We get so we get dq ds, this one, and of course we can also just divide by ds and dz. So we get dq ds plus that thickness times sigma z dz is equal to 0. And then if we do our equilibrium in S direction, what we get is dq dz plus t times d sigma ds is equal to 0. So we can get two equilibrium equations. So we're going to continue with just looking at focusing on z direction. This is just for it to be complete. So we still have to answer the question as how do Q and the shear force, external shear force, relate to one another. For that, we go back to our original statement I made about like statics. Let's have a look at basically a small piece in statics. In equilibrium, we can define an element somewhere in our body. We can call that element as a certain delta z or dz. And we know that we can have a force applied, a shear force in Sy. We can have a moment around x, mx. And then to be in equilibrium on this side, we must have Sy plus the variation of Sy with respect to delta z, dz. And on this side, we must have mx plus delta mx with variation in z multiplied by the differential element z. And we're looking at a distributed load we can have as well. So it's a unit force per unit length. So this will be our Q. So this will be in small incremental element in any beam, for example, or any structure. We can identify such an element. And what we can do again is we take the variation, or we take the equilibrium equation, and we identify that. So let's see. Let's do upwards positive. So we get Sy, this segment, delta Sy with respect to delta z, multiplied by our differential element of dz, minus Sy. And since there's a force equilibrium, we can ignore the moments, and we can relate that to plus Q, which is our unit force, force per unit length, multiplied by dz, since there's our length. It's equal to 0. And what we say here is, first of all, these two terms cancel, dz's can cancel out, then we can get that Q is equal to the variation of our shear force with respect to z. And this is force equilibrium.
Should that be negative?
Yes, it should be negative. And now we can do the same thing, but for the moments. And then we get this, so we take a moment around, say, a point A. If we have an axis system, we can define this as point A. Let's define this as dy, so we'll need that. And then we can get as mx plus delta mx dz. Since this is clockwise, this is negative, plus counterclockwise is positive, so x. And then, of course, this will also create a counterclockwise moment. So sy plus this delta sy blah blah will create a counterclockwise moment. So again, positive. So we get sy plus delta sy dz, and this moment arm is equal to dz. So we can add dz, and then we can rewrite this distributed force as a force in the middle multiplied, so equal to half q dz, and that will have an arm of half dc as well. So we get as the q force multiplied by dz, and that's equal to, well, the moment arm is equal to dz over 2, and that's equal to 0. Yeah, it's visible. So again, a couple of terms will cancel out. So we know we have an mx, we have plus mx here, so these cancel out. Let's see what else cancels out. We can divide by dz, since we have a dz everywhere at least. So 1 dz cancels out. And then we can collect the terms, and we'll get that then for simplification, delete this. We get sy plus sy washed out the shear force with z multiplied by dz plus q dz over 2, and we have a negative. Is that correct? Yeah. So this becomes negative. The moment x with respect to dz is equal to 0. So the next thing what we assume is that this differential element basically goes to 0, because you want to have this basically a point derivation. So we take dz goes to 0. So what happens? So basically everything with dz basically becomes, you can basically neglect every term with a dz in it. So you can ignore, in this case, the variation of the shear force with respect to z multiplied by dz, which goes to 0. We can ignore this part. We can ignore that the variation of the unit, the shear flow multiplied by dz over 2. We can ignore this to 0 as well. And these two are just variation. So this one we cannot ignore because it's not multiplied by the element length dz, but just a variation on z. Okay. So what we get is that Sy equals to the variation of the moments in x with respect to z. And just keep in mind, even though we have here over 2, if dz goes to 0, it just goes to 0 as well. Okay? While we have here dz.
So if dz is approaching 0, should the differential change in the moment should also approach 0?
The moment can be a function of z coordinate. So so the variation of in z doesn't have to go to 0.
What if the
differential element of z goes to 0? So the moment arm becomes smaller and smaller and smaller. So basically, if this goes to 0, this contribution that you multiply by in length goes to 0. So this drops. But the variation of this function with respect to z doesn't have to go to 0. Okay. So what we now can do is we're going to take this term, and this term, and combine it together. So let's simplify our equations. So now looking at it in shear flow, so when at shear flow due to a shear force, we have the following. We have that the variation of shear flow with respect to S is equal to, or plus, the variation of the direct stresses with respect to Z is equal to 0. And we also derive that Q is the variation of the shear force with respect to Z. And we also got that the shear force is equal to the variation of moments with respect to Z. So what we next do is basically we recall our equation from direct stresses, because this is what we already have derived in our bending, an equation for direct stresses as a function of moment. Here we have a relationship between the moment and a shear force, and here we have a relationship between shear force and shear flow. So basically, by using those three different components, we can combine it into one component where we can identify shear flow as a function of our shear force. So we're going to recall this. So recall our direct stresses equation. And that one was sigma z is equal to my I xx minus mx I xy. ix I by y minus my ixx ixy, sorry, ixx I by y ixy squared multiplied by y. So this was our equation. And now let's basically substitute, since this is sigma stress with variation of with respect to z, we can basically substitute, take this equation and take the variation with respect to z. So if you take the variation with respect to z of dz of sigma z, sorry, we know that these are all cross-sectional dependent terms, so they cannot vary with z. So the only thing that can vary with z is basically our moment. So we get here my with respect to dz. Mx dz x dz and my dz, because that's the only thing that can vary with the function of z. So the variation of direct stress with z are dependent on the variation of the moments with respect to z, and of course the remaining moment of inertia terms. So now we can use our first substitution. We know that Sy is equal to mx with respect to z, so we can substitute that here. So we can say, and of course, and this is Sy is equal to the variation of moments around x. So Sx is the variation of moment around y with respect to z. So we can get that shear force in x, Ixx, minus shear force in y, Ixy, Ixx, Iyy, minus Ixy squared, multiply x plus, and then we get here Sy Ixx minus Sx Ixy and there's a variation of direct stresses with z as now, instead of function of variation of moments, we have a function as shear forces that are applied shear forces. So Sx applied shear force in x direction, and Sy is applied shear force in y direction. Good. So now we can back substitute this equation into here, and now basically we have a function for the shear flow as function of our shears, applied shear forces here. So what we do is we first have to multiply by t, because this one is multiplied by t. So we multiply by t here. We get a t here and a t there. And what we then can do is just take this to the left hand side, so it becomes a minus. So we get equal to, so this basically becomes a minus. What we just do is take the minus, put the minus in front of it. It's a bit easier. Sx Ixx minus Sy Ixy Ixx Iyy minus Ixy squared dx plus, see, now let's keep that in minus. So this minus becomes Iyy. Double check. Yeah, it's still visible. Ty. Ty. And Ixx, Iyy, Ixy squared. So this is of course a partial derivative. So if you want the shear flow, we can just take the integral. So in this case, Q is equal to the integral. And since we're taking variation with S, our integral goes from 0 to S. And then we have to identify a couple of more things. The applied shear force does not vary with S. Only Tx and Ty do, or the coordinates X and Y. So what we can do is rewrite this as Sx, Ixx. But I'm going to rewrite this as just delta. A bit easier. So over delta, and then becomes 0 to S Tx minus Sy Ixx minus Sx Ixy over delta, the integral from 0 to S Ty ds. So this is our final equation of shear flow. So we can spot that our shear flow is a function of our shear forces, applied shear forces. So those are basically given applied loads. They do not vary with S. So basically a length pad around the cross section. Our geometry cross-sectional properties like moment of inertia do not vary with our location of the geometry and our cross-section. So those are taken out of the integral. The only thing that can vary is basically thickness and the X location. So with that said, I'm going to go to the lecture slides and we basically can do a quick recap. Okay, so previously we looked at solid beams. That was basically the bending what we looked at, and we're going to continue from there on. We said by just making our life a bit easier when we're talking about shear, we want to look at a concept of shear flow, which is equal to shear force per unit length, because it can make our derivations a bit easier. And we looked at basically a cross section or an element in any cross section. We started doing the equilibrium equations both in the X direction or in the Z direction and S direction. And we could come up with an equation that states the shear flow plus some part of our direct stresses must be equal to 0. And then when we went out, we want to do a couple of things. We want to equate our shear flows to our shear forces, and at the same time want to also equate our shear forces to our bending moments. That's what we did. And once we did that, we could reintroduce our bending stress equation, and we could basically take the variation with Z. And we noticed that the only thing that can vary with Z are actually the applied moments. The cross-sectional components like the moment of inertia cannot vary, so those remain constant. And we realized that the variation of direct stresses with Z equals to the variation of the moments and the other terms. So noticing that the shear force in X is the variation of the moment in Y with respect to Z, we could basically substitute that back, and now we have our direct stresses as a function of our applied shear forces, Sy and Sx. Again, we went back to our equilibrium equation, we substitute that back in, and then we take the stresses to the right hand side, and we take the integral from 0 to S, where S indicates the boundary where we take the integral from. So if you can look in this example here, we start at a certain location, and then we take the integral bounds starting from that location. So S here is basically your path that you travel to. That small segment S, where we multiply by our shear flow to get our shear stresses that we started off with. So in summary, that's the equation we have. And of course, if we have symmetry, IXY, so all the applied rules and all the applied knowledge that we got from bending still applies. So when we have symmetry, IXY is equal to 0, so it simplifies. And when we have only one shear force given, mostly SX or SY, sorry, then the equation simplifies even further to negative SY over IXX multiplied by the TY ds. Yeah, let's do a small example. Let me see. Yeah, so determine the shear flow distribution of this thin wall Z section due to shear load SY applied through the shear center. And the concept of shear center is very important, but we'll get to that in the next lecture. So let's quickly draw that up. So we can already make a couple of assumptions. Let me see. So we know that this should have taken an easier one. We know this cross section is not symmetric. So we know that we have to calculate all the three components of the moment of inertia, IXX, IYY, and IXY. However, we are not given any shear forces in X, so we can reduce our equation a bit. So our shear flow equation becomes Q is equal to SY IXY over IXX IYY minus IXY squared, 0 to S dx ds, minus SY IXX IXX IYY IXY squared, and 0 to S ty ds. So let's draw the figure as well on this side. Let's try it on this side. This is h over 2 stage as the centroid here, 0.1, 0.2, 3, 0.4. And we have an SY here, and the thickness is T everywhere. Okay, so this is what we have. So first step, let's calculate the moment of inertias, IXX, IYY, IXY. I would just give them because that's basically IXX. I would do them at home if I were you, just to verify. So notice we use the thin wall assumption. So we have to basically ignore t to the power of 3 for segment 1, 2, and 3, 4. We just use the standard terms. So we can, let's define this term here as delta again. And if you just plug it in, what we get is h cubed over t, or multiplied by t, 1/3 multiplied by 1/12 minus 1/8 squared. So this becomes h is 1/36 minus 164. What's the common denominator? 6, 4 probably. 9 minus 16. Right. So this becomes 16 times 16 is 90 times 6 is 36. 126 minus 9, 126 h cubed t, and then we'll get what's that? 16, so 7. I think this is it, but it doesn't really matter since it's a denominator. But this what would determine what we will have, and we can basically plug in this into the equation. So what we get is q. Since this is all known quantities, we can just plug a number into it. It will become a bit easier, and then we can work from there onwards. So this will be 70162. This will have an h cubed t in it, so the h cubed t basically disappears. So as we apply both of them with h cubed t. And if we do this correctly, what we will have left over is sy on this side. So sy and then we get 0 to s 10.29 x minus 6.86y ds. Let me check one thing quickly.
You can simplify the delta to be 1 over 18 h cubed times t.
1 over 18?
Yes, sir.
Perfect. In my solution manual, I have h cubed here, so I'm thinking of how that's possible. Because we have h cubed over here, we have h cubed over there, so that would cancel out. So I might have incorrectly stated that in the lecture slides. I'll double check for the next lecture to be on the safe side. But important is that we get the following equation out of it. So we know that the shear force is dependent on our shear flow is dependent on our shear force, and the location of our pad S, and the coordinate system x and y. So now the trickiest part in shear flows is basically getting this part correct, this integral part. So what does this integral from 0 to s mean? So you start off with a certain location. So this is your S1, this is your S2, and you go around your cross section. So you always want to start at a free edge. Why a free edge? Because you know the stresses there are basically equal to 0. The stress is equal to 0, our shear flow is equal to 0. So we know at location 1, our shear flows is equal to 0. So now we test that can be an easy starting location. So if we would evaluate that Q at location 1, then they should be equal to 0. And then we start propagating along our cross section. So how does this function? How does this pad S vary as a function of x and y? So in section 1, 2, our pad S varies as follows. So we know that the variation only occurs if this is our y location and this is our x coordinate from the centroid. We know that the y location remains constant. So in this case, from 1 to 2, y is equal to a negative h over 2. Keep in mind that these x and y locations on your cross sections are with respect to the centroidal axis of that cross section. So here we're going basically from we remain at the y location remains at negative h/2. So how does the x vary? Well, x varies along your path s. So here at this location at 1, so x1, this coordinate refers to negative h/2 as well, just by coincidence. And at x is equal to 2, it equals to 0. And we vary with the function with s1. So the function of x as function of s is negative h/2 plus s1. Is this clear? Because this is basically where all I would say 80% of the mistakes come in. And then define the correct integration bounds, and then define how x and y vary with your path s. So we say here that our path starts from 1 to 2. So if I'm walking along this path, I know that at my y location I remain constant at h/2, but my x location varies from negative h/2 to 0. So my function of s in the x direction is equal to h/2 plus s1. And my integration bound goes from 0, from point 1 to point 2, which is basically going from 0 to h/2. Okay. We basically ran out of time. So what I would recommend is we start off with doing this. We got this far. Try to complete this assignment at home, and then next week we basically repeat this exercise as well. And there will be a couple of errors. I think Maxon will derive this equation here as 10.32 x minus 6.84y. And I think there's just a couple of rounding off errors that he uses in this step here because he uses decimal point. So do this assignment at home, and then we will we'll continue from here. And again, with shear flows, majority of the problem occurs by not identifying the correct paths for x and y, and not being able to identify the correct integration bounds. So we will focus heavily on that. Okay, are there any questions? No? Okay, perfect, thank you. I'll see you next week. So Thursday is no lecture.